welcome everyone. So, we are discussing on high level synthesis, and in the last class we have discussed about this the steps of the high level synthesis using an example. We just understand what would be the sub steps of high level synthesis, and today's outline is something how we can automate those sub steps, like basically scheduling, allocation binding and data path and controller generation. Right. So, if you just look back into the high level synthesis steps, we have seen in the last class that starting from an initial behavior written in C or something, it go through pre-processing, scheduling, allocation binding, data path controller generation, data path generation and controller generation. Finally, we will get this RTL, right. So, we get this RTL out of that C code. And so, what we have discussed in the last class is not how to automate these steps. We just talk about what is the logical next step, right. So, that we have just tried to understand through an example. Today, we are going to discuss about those steps in the automation of those steps. Okay. So, pre-processing is also part of that, and how do we, as we discussed in the last class, we apply extract and data and control flow graph out of this behavior, and also do the data dependence analysis. Those things are very conventional compiler transformations. So, we can assume that those things is already known to the audience. But we also discuss about that this in pre-processing steps we apply a lot of compiler optimization techniques that improves the synthesis results. That will be a separate class. Okay, we will discuss in a separate class about that. So, today we are mostly going to discuss about the automation of scheduling, allocation binding and data path and controller generation. Okay. So, we will move on. So, before moving on, we know about this graph. This is the data dependence graph, where we have the dependency we have discussed in the last class, how the dependency you can extract. And just to convert this into a sequencing graph, what we just do, we just add a source node and a sink node, and we connect all the input variable to this node and all the output variable to this node, sink node. Right? This is source node and this is sink. This is just to make the scheduling process a little bit smooth. This is nothing much. This is just a operation, no operation kind of thing. Right? NOP means no operations. So, we are going to talk about this scheduling in this sequence graph. It is nothing but the data dependence graph, right. And we are going to talk about take the same example to discuss all the algorithm that we are going to learn today. Okay. So, the first and the easiest of scheduling algorithm is ASAP. What is that? Is as soon as possible. Okay. So, as the name suggests, is something we try to schedule the operation as soon as possible, right. So, if you just remember in scheduling, what we do, we just try to assign time step to the operations, right. Initially the operations are untimed, we assign time step to each operations, right. For example, this operation is scheduled in time step 1, this operation is scheduled in time step 7, this operation is scheduled in time step 3 and so on, right. So, we have to assign time step to the operations without violating the data dependency, that is our target. So, to do that, we first, the easiest algorithm is ASAP, which is nothing but as soon as possible. As I mentioned, whenever some operation is available, we schedule it. What does it mean available? Available in the sense either this operations, the operation on which it depends is already executed, or it depends on some variable which is available, right. So, that is what is called as soon as possible. So, let us look at the same example, the differential equation solver example that we have discussed in the last lecture. That initially you can see this operation depends on the variable. So, this is available. So, this is basically available. This is also depends on variable. This is also available. This also depends on variable. So, this is also available. This is also depends on the input variable. So, this is also available. This is also available. So, I am going to schedule all these 5 operations in the time step 1. So, that is what I have done, right. So, these operations are scheduled in time step 1, right. So, this is time step 1. Similarly, once this is done, this operation is now available, because the dependent operation is already executed, this T1 is now ready, this T2 is also ready. Similarly, this is also available because the precedence operations are done. Similarly, this. So, in time step 2, I am going to schedule all these 3, right. So, this is what I have done, all these 4 in the sense, because this 1, 2, 3 and 4, because this is also done, because this is also done. In the next step, this can be scheduled because this predecessor operation is now executed, and then 4th step I am going to execute this. So, effectively I am able to execute all this operation in 4th time step, right, 4th time step. So, this is what is called as soon as possible. So, this just overview of the algorithm, what is just whenever there is a, so I start from the time step 1, whenever there is an unscheduled node exists. So, I will just going to select those predecessors already selected. So, I am going to select one of the unscheduled node whose all the predecessors are already scheduled, and then I am just going to assign a time step to this based on the maximum of the all the predecessors, right. So, for example, if you just look into this, when I am going to schedule this this operation. So, this predecessor is scheduled in third time step, this is in time steps 2. So, the time step I am going to assign is 4, maximum of these 2, right. So, this is what I am doing here for all this node, just assign this max of this. So, what is that? Ci is the number of time it takes to execute that particular operation I. So, we will discuss on more. So, so far we assume that all operation will be single cycle operation, that means operation can be scheduled in one cycle only, but there may be some operation which can be scheduled in need more than one clock step, we will discuss later. So, what is the advantage of as soon as possible algorithm? This always give you this minimum latency, right. So, the number of time step that will be given by this is minimum. So, latency is nothing but the number of time step. Okay. Latency is nothing but time steps. Okay. So, the advantage of as soon as possible is that it always give you the minimum latency, that means the minimum number of time steps required to schedule that particular set of operations. Okay. And this is kind of an optimal solution, because we cannot have a less time schedule which is can have less time step than this whatever is given by this as soon as possible. But this is unconstant, that means the number of resource required here is there is no control over this, right. It always give you the maximum number of resource possible. For example, if you remember in the last class, this particular example we actually able to schedule in 4 time step using 2 multiplier, right. Now, you can see here there are 4 multipliers scheduled in time step 1. So, I need at least 4 mult to execute this operation in hardware, right. So, that means it does not give you the optimum resource, but it gives the optimum latency or the number of time step. So, this is kind of unconstant schedule, but if you I ask you to use only 2 multiplier, then this particular algorithm will not work, right. So, that is something that is as soon as possible. Okay. So, similarly, we have this as late as possible is just the opposite version of this as soon as possible algorithm. Here we are going to try to delay the operation as late as possible, right. So, here we will have a given a latency bound, that means I want to schedule this particular thing in say k time step or say 4 time step, and whether this is a feasible or not. So, if the latency is given too small, then the solution that we are going to get may not feasible, right. For example, if I give for this example, as I understand, at least 4 time step is required, but if I ask you to schedule this in 3 time step, this is not feasible, right. So, assuming that all multiplier is a one cycle operation. So, that is something is not feasible. So, if you just apply this as late as possible algorithm, here the solution may not exist, because if you give a very less latency bound, right. So, here the algorithm is similar to that ASAP algorithm. What it does, it try to schedule the operation as late as possible. So, if you go into this, we try to start from the output. So, those operations that are generating output, right, these operations. So, they are generating. So, they has to schedule in the last step, right. After if you do not schedule in the last step, you need one more time step, right. So, we have to schedule all the operations that are producing output, right. So, we have to schedule these operations in the last time step. So, here it start with a latency bound. So, latency bound is C t. So, it will start from the last time step. So, if I, for example, if I ask you to schedule this behavior in 4 time steps, so latency bound is given 4, right. So, if you given this 4 time steps, and then I will find out all the variables that are producing output, we are going to schedule them in the last time step, 4 time steps. So, I am going to schedule these operations in 4 time step V8, V9, V11, right. So, once they are done, the operation that are actually depend on this operation on which they are now ready to be scheduled. If you do not schedule here, you need one more time step, right. So, we are bound to schedule all the operations that the result of that operation is used by these operations, right. So, now if you look into this behavior, it is very clear that now V7, V6, V4 and V10 has to be scheduled now, because they are now ready. Right. So, I am going to schedule this V7, V6, V4 and V8 in time step 3. Then I reduce the time step by 1, and then I will find out these 2 operations has to be scheduled, because they are the next. So, I schedule it here, and then finally, I have to schedule these 2 operations in the first time step. Right. So, this is how what is the ALAP operations give, right. So, if you go look into the algorithm, I will again the same process that unscheduled node exists. I will find out those node whose successor has already been scheduled, right. So, here I try to find out this node whose successor is already scheduled. For this, their output is already scheduled, that means they are producing output. So, their output is already scheduled. So, I am to find out those number of operations and then I am going to assign their time step mean of their predecessors, I mean successors, sorry. So, for example, here if you try to find out the time step of this, its successor is this time step assigned is 4. So, I am going to make it 3, right, assuming this C is 1 here, right. So, if you have C say 2 or 3, then if it is say 5, then it will be, this is 2, then it will be assigned 3, right. So, this multi cycle operation I will come to come later. So, this is how this algorithm works. So, this is also very simple algorithm. So, discussion on this ASAP and ILAP, as I understand say, these are mostly do not consider the resource bound. So, it always generate a minimum latency synthesis, but there is no control over resource. The kind of synthesis result we are going to get will be not resource optimized, right. So, that is something, but the good advantage is that it give a latency bound. So, the ASAP solution or ALAP solution, whatever that bound will get, that will be the minimum. So, specifically ASAP will give the minimum latency bound, and that will be the minimum number of latency that we can obtain from this ASAP solution, right. So, there is another important aspect we can utilize this ASAP and ALAP algorithm to find out the mobility of a operation. What is that? So, mobility is something, if you just go into this, here you can see that this is my initial graph and this is my ASAP schedule, this is ALAP schedule, right. Here this operation schedule in time step 1 in ASAP as well as in ALAP. So, this operation has to be executed in time step 1, there is no other alternative. But if you look into this operation V11, this is scheduled in time step 2 here, it is scheduled as 4, right. So, you can either schedule it 2, 3 or 4. So, there are mobility of 4 minus 2, which is 2, right. The mobility of this is something, the range of time step where you can actually schedule this particular operations. For example, here V11 can be scheduled here, here or here, right. This is the range from time step 2 to time step 4. So, from this ASAP and ALAP, we just define from that you can actually calculate the this mobility of each operations, right. So, if you just see here, these are the operations they are actually have a different time step. If you just calculate them, you can actually get this mobility of each operations, right. So, these operations, for example, V11 I just discussed, it is 2. If we just take V8, V8 is here is time step 1, here time step 3. So, 3 minus 1 is 2. So, similarly, you can actually find out this mobility of each operations. So, what is the importance of this mobility? The importance of the mobility is basically you can actually have a relaxation on where you can actually schedule this particular operations, right. For example, when you have a resource constraint, right. So, where you have the constraint that you cannot execute this operation with more than 3 multiplier or something, and if you have a mobility and if it is causing a problem, you can actually delay that operation to the next time step. So, that you can actually improve your resource utilization. For example, here, so here there are 4 multiplier, but if you just move this to this and this to this, because they have the mobility is more than 1, you can actually use 3 multiplier, right. So, this is something we can utilize. So, this particular relaxation we can utilize when you have a resource constant, try to generate a minimum resource, we can utilize this mobility factor of each operations. So, that we can reduce the number of resource, right. So, this is something also an useful features of this ASAP ALAP. And another important factor of this ASAP and ALAP is they are basically polynomial time algorithm, right. So, because you can actually use topological sorting. Topological sorting is something where if you have is a sorting of the nodes of a graph. If you have a edge from a Vi to Vj, then the sorting order Vi will always come before Vj, right, and this is true for all possible such edges, right. So, then this is come to a topological sorting, and those nodes are there in the start, we can actually schedule them first, right. So, you can actually use topological sort to do this operation efficiently, and this topological sort is use nothing but this graph DFS, depth first search algorithm, which is complexity order of V plus E, right. V is the number of vertices and E is the number of edges. So, these algorithms are polynomial time and they have given minimum latency bound, but without any resource constraint, right. So, this is something the very simplest one of the algorithm. Okay, now, we will if we just move on, as I discuss your algorithm in your circuit may have different kind of complexities. First of all, you might have resource constraint, right. So, if you have resource constraint, that means you cannot use as much as possible resource, you have to schedule everything with a resource bound, right. So, if you have that, then ASAP ALAP won't work. Even as I mentioned earlier also, if you have operations can be of different type, it can be multi-cycle, it can be operation chaining, it can be pipeline. This example clarify this. So, for example, suppose this is the schedule that is generated by some algorithm, say ALAP or something, and your multiplier take 30 nanosecond and this adder is taking 10 nanosecond, right. So, if you have this, the what will be your clock period here? It has to be 30 nanosecond, right, because your clock either have 10 or 30, you can have both. So, you have to decide that your clock period is something of 30 nanoseconds, right. So, that means, in this particular schedule, you can see that 20 nanosecond of the time this clock period is remain idle, because we are not doing anything. Similarly, here, but only because I have to execute the multiplier in 30 nanosecond, I need that clock period. What will be the alternative? The first alternative is multi-cycle, right. What we can do? We can define that my clock is of 10 or say 15 nanosecond, and I can execute this in in one clock, this also in one clock, but I decide that I execute the multiplier in two cycle. So, that now from 30 nanocycle clock I go to 15 nanocycle, even you can do it in 10 nanosecond period also, right. So, you can do adder here, multiplier subtraction here, nothing here, and you can execute the multiplier in 3 clocks, right. So, this is also you can achieve 10 nanosecond also using multi-cycle. So, this is another variation. So, you cannot always the case that your multiplier or any operations is always a single cycle. To get a high clock speed, sometime we decide to use a multi-cycle. For the bigger operations, we use a multiple clock cycle to execute that particular operations, whereas the smaller operation can be executing fast. So, this is one option, or other way you can actually you can skip your clock period 30 nanosecond, but you try to execute both of them in the same clock, right. Then also you can achieve 30 nanosecond, right. So, in 30 nanosecond clock period, right. So, that is also possible, and the third possibility is the pipeline. So, you execute this in parallel, you know the pipelining concept. Yeah, so, this is started after first phase of this, I will start the second multiplier, and then once so in the second clock, the second part of the multiplier will be executed, whereas the first part of the second multiplier will be executed. In the third clock, the last part of the multiplier will be executed, the second part of the second multiplier and the first part of the third multiplier will be executed, right. So, this is how the multiplier works. So, after 30 nanosecond, first output will come, but after every 10 nanosecond we will get another result. So, that is also another possibility. So, now the question is, if you have all these complexities, like you have resource constraint, you have this multi-cycle operation, pipeline operations, or say operation chaining is also possibility, what will be your good scheduling techniques, right. So, that is something we are going to discuss. So, that is what is called constant scheduling, right. You have a constant scheduling. So, what is constant scheduling? As I mentioned, it can have different kind of constant, and you can have two different versions. You try to minimize the latency given a resource constraint, or you try to minimize the resource given a latency constraint. So, I have MLRC, minimize latency under resource constraint, or minimize resource under latency constraint. There are two variations of the scheduling algorithm, right. And in general, both the problem are NP complete. What is NP complete? NP complete in the sense, those problems whose solution cannot have, do not have a polynomial time deterministic solution, right. So, that means whatever the algorithms are there is exponential. So, so in this kind of NP complete problems, if you have exponential algorithm, say n to the power k or 2 to the power k, is very expensive, right. If you have a bigger algorithm, it won't work, right. If you just try to write an program in C, say which is say 2 to the power n kind of algorithm. So, if your n is going beyond 40 or 50, your algorithm will never terminate, right. So, it takes a lot of time. So, we try to find out some heuristic algorithm. Heuristic is what? We try to find out some logical consequence, logical decisions which result in some good solution most of the cases. Instead of going for exact solution, we try to go for a heuristic based solution, right. And exact solution also is there. We can use integer linear programming algorithm or whose algorithm. Okay. So, we will try to discuss one exact solution and one heuristic based solution in today's class. and since this list scheduling based on the idea of this Whose algorithm, we will just briefly discuss what is Whose algorithm before going to this. So, in the next 20 minutes or so, we are going to discuss ILP based scheduling algorithm and list scheduling. Okay. So, so before going to this modeling your scheduling algorithm instead using NLP, sorry ILP, integer linear programming, let us define that what is integer linear programming, right. So, here you can see you have a minimization factor where you have set of variables x 1 to x n and you have this constant, constants are there. So, you try to minimize this value of this subject to satisfy all the variable value of this variable, try to find out the value of this variable such that it satisfy all this constant and give the minimum value of this, right. Where C is a constant vector, B is also a kind of a constant vector, right. So, B is also a constant vector. So, this is something the formulation, and if your variables are continuous, then it is a linear programming solution. If your problem this variables x 1 to x n are integer, then it is a ILP. Okay. So, let us take an example. For example, suppose I have the variable x 1 and x 2 and my objective function is this. I want to maximize this value of this minus x 1 plus x 2. So, if you and you have the constant this, these are the two constant 2 x minus 2 x 1 plus x 2 is less than or equal to 1 and x 1 plus 2 x 2 is less than or equal to 5. So, the value of x 1 x 2 should satisfy both this constant and generate the maximum possible value of f, right. To model this, your C is minus 1 and 1, because this is minus 1, this is 1 and this is your variable. So, this is your this C t into x transpose of this, and your constant is this a x minus b. So, your these constants are nothing but this. So, you can see your a is nothing but minus 2 1 1 and 2 and this is your x 1 x 2, right. So, this is how this this a x less than equal to b, right, and this is less than equal to nothing but 1 5, right. So, this is how we model this problem. So, so if you just plot this variable, you will get this this line. So, this is the solution space, right. This yellow part is the solution space and we try to find out the maximum value of this, right. So, if you just put the value of this x and y this value, then we get f equal to 0. So, if you just give the value of f 1 is this, say something like 1.8 and this 1.1 or something, I will get f equal to 1. But if I give the value of x is 2.2 and 0.8, then you will get the maximum value, right. So, that will result in my 1.6. So, that is the maximum possible value of this. So, this is how the whole thing is works. So, we try to find out solution space and then try to find out the maximum value of this, which will give you the maximum of this objective function. So, now we are going to model our scheduling algorithm instead using this. So, we have to find out what are the variables we need to model your scheduling problem to this and what would be your constant, right. So, these two we have to find out. Let us discuss. So, for our ILP modeling of scheduling, we are going to use a variable xil. Okay. So, what does it mean? xil is 1 means variable operations vi start at time step l, right. So, xil is equal to 1 if that particular operation start time of that particular operation vi is l, otherwise it is 0, right. So, if you just assume you have operation is v 1 to v n, the operations are v 1 to v n and say time limit is lambda, then your lambda can be 1 to lambda plus 1. So, how many variables are there? So, operation v 1 I have x 1 1, because it can schedule this x 1 2 x 1 3 into x 1 lambda plus 1. That means, operation if operation v 1 is scheduled in time step 1, then this will be 1, and if it is operation 1 scheduled in time step 2, then this will be 1 and so on. So, I have this number of variables for operation v 1. Similarly, for v 2 I will have a variable like x 2 1 x 2 2 to x 2 lambda plus 1. This way v n के लिए x n 1 x n 2 to x n lambda plus 1, right. So, these are the possible variables I have, right. So, these are the possible variables, right, n into lambda plus 1. So, these are the number of variables and we have defined this is 0. So, only if that particular operation schedule on that, right. So, we have to find out those values, right. So, these are the variables, the value of these variables has to be find out, right. And now what are the constant I am going to use? The start time of each variable is unique, right. So, for that means what? You cannot start a operation in multiple time step, right. It has to start in some time step, right. So, that means only one of this n lambda plus 1 variable can be 1 for V 1. Similarly, this for representation V 2 exactly at most exactly one of this lambda plus 1 variables will be 1. Yeah. So, as I mentioned that maximum of this n lambda 1 variable only one of them will be 1, right. So, that is that given by the unique start time, that summation of this x 1 I L for I equal to 0 to n or will be 1, right. And now, if you just go back to your ASAP and ALAP solution, a operation ASAP will give you this minimum time step. After that, it has to be executed by that time step, it cannot go you can go beyond that, because then the dependency will be violated, and ALAP give you the last possible schedule, right. If you try to schedule it after that, then your number of time step will increase. The span, that lifespan, this mobility is something from the time step where the ASAP schedule and where ALAP schedule, right. So, now you can actually say I do not need to consider all other, obviously this other variable will be 0, only the time variable that is between this time step TIS to TIL, which is nothing but the time operations where ASAP is scheduled and this ALAP is scheduled, around that variable only this particular variable can be 1, right. So, that is, so you can rewrite this expression in this summation from TIS to TIL, the mobility span, right. Other time step, it is obviously this other variable will be 0. So, we do not have to consider those. So, we just simplify this expression into this, right. So, this is the first possible constant. What is the okay? Now, that is also very important. So, even if I just as I mentioned that for variable this L equal to TIS to TIL from this ASAP to ALAP, this x IL equal to 1, right. So, this is what I assume. So, that means this operation will be must be scheduled at least one of the time step, only this variable x IL will be 1, only one of the variable from this range will be 1, right. And now, suppose this is scheduled in say time step k, right. So, what will be the, how do you represent that your start time Tj, say for operation say Vi, start time is say Ti, right. So, how can I represent this Ti is L into TIL. So, this is the summation. In this summation, I just multiply this L, right, because now if this particular operation is scheduled in L or say time step k, then only that particular k will be 1, all other will be 0. So, if I multiply that with this k value, then it will give you the k, right. So, the start time of the particular can be represented by L into XIL, right. So, this is how I can find out the start time of this, right, because now I have to represent everything in terms of this variable, because these are the only variables I have and I have to make the model using these variables only. Okay. So, now this is something the start time. Now, first I just mentioned the first constant is the start time must be unique. So, which is given by this constant. Then I have to find out the precedence relationship must be satisfied, right. So, for example, suppose you have a age from Vi to Vj, Vj to Vi, then this and say this will take say dj time step, right. So, cycle of the number of time step required to execute this is dj. So, it is so dj number of time step. So, if this is start is tj and the starts time step of this Vi is Ti, then Ti must be greater than equal to Tj plus Dj, right, because you cannot start unless this operation is executed, because there is a dependency. So, if it is start at Tj, it will take Tj Ti this Ti plus Dj minus 1 basically those number of steps, and then only the next step I can only schedule this, right. So, this is the timing constant corresponding satisfying the precedence relationship. And if I just represent this Ti by this, it will give you this L into Xi, and if I just represent Tj, it will give you this, right, T into JL, right. This is IL, this is JL, because this is nothing but the operation Vi and Vj, and this is Dj. So, this is what I am going to get it for the precedence relation. This is for all possible edges. I just discuss it for one edge, and this is for all possible edges. I will get this kind of constant. So, which is actually has to be satisfied, because whatever the schedule you are going to get, this has to satisfy this precedence relationship, and this is given by this set of constant, right, the equations. and how many such equation will be there? One equation for each edges. So, the number of such equation will be the number of edges in the dependency graph. Okay. And the third set of constant is nothing but that resource constant. Okay. What is resource constant? So, if you just mention that I mean if you have some resource constant, that means you may specify I want to execute this using 2 multiplier or say 3 multiplier, how to put that particular factor into this constant solving scenario, right. So, suppose I assume that a operator type k has a k number of instances. This is nothing but a multiplier has say 2 instances, right. So, so now since my operations are multi-cycle, at a particular time I can have only k number of multiplier active, a k number of multiplier will be active at a particular time step, and that is given by this constant, that whatever this value I will discuss should be this define the number of multiplier required in any time step. So, time step I, time step L should time step M should be less than of a k, right. So, what is this signifies? Since now the operations are multi-cycle, so if some operation started somewhere early, that may be also continuing in this time step, and this some operation may start here, right. So, if you just go into this, some operation may, if you just think about the time step 6, some operation starts here, some operation may continue here and started early and continuing in this time step, or some operation started too early and is going to finish here. So, all these 3 are active in this particular time step, right. So, I need at least 3 multiplier to execute this these 3 operations. There are 3 so, I mean if this is the scenario, then I need 1 multiplier to say this is a V1, this is a V2, this is a V3. I need say 3 multiplier to execute this in time step 3, right. So, if you have, so whatever the resource constant is given to you, so I have to consider all these 3 scenarios, and summation of this should be less than of the number of multiplier is specified, right. The operator is given. So, if you make it generic, so if you are considering the time step L, some operation start point here or start next previous state or till di L minus di plus 1, right, because this is a Vi operation and it takes di number of cycle, it might start here, still this will end. These are the all possible scenario, right, and all these scenarios, so summation of all these scenarios should be less than or equal to a k. Right, this is what is given by this constant, that this is for the multiplier specific types. This is operator type k, the time step. So, I have to consider all that operations that started from L minus di plus 1 to L, because those are active in time step L, right, because I am now concerned about the time step M. So, in M all the operations that are started till this L minus d plus 1 or to this previous step, all are active. So, for all of them I need a multiplier. So, all these active operations should be less than or equal to a k. So, these are the 3 possible constant. One constant is this unique start time, next constant is to maintain the data dependency, and third constant is to maintain the resource constant, right. So, this is the set of constant, and now so what is the overall problem? So, I have this. So, my now this this is my, so if you have the latency minimization, this is minimize latency under resource constant, then my objective is to minimize this factor which is C by T, and T is nothing but this start time of these operations, right, this start time of the operations which is nothing but this start time of these operations of all the operations. So, if I just give you this value, so this T would be of size n, right. So, some T1 to Tn, where the Tn is the start time of the operation n, and T0 is the start time of operation V0, right. So, that will give you the start time of Vn, right. So, this is how the whole thing works, and now this constant is now we have to decide what is the constant value, right. So, now if you want to minimize the latency, what will be the constant value? I am going to consider this Cn all 0, only the last one is 1. Why? Because I want to get the minimum latency, that means I want to schedule this Tn as soon as possible, right. So, that is the minimum value of this Tn will give you the minimum latency, right. Other value I am not care, right. But if in the ASAP solution I want to minimize that, I want to schedule all the operation as soon as possible, then your C will be nothing but all 1, right. So, all operations try to find out the minimum value minimum start value of that particular operations, right. So, this is something for ASAP C will be this, for minimum latency MLRC problem the C will be 001, right. So, 00 last bit is 1. Okay. So, here is a summary. I have this start time T1 to Tn, I want to minimize this Ct, where this and I have the constant 1, this is the unique start time, this is the data dependency and this is the resource constant. So, this is subject to this, I want to minimize this value, where C is for MLRC, this is nothing but 0 0 to 1, right. So, this is how the minimum latency scheduling under resource constant is modeled, right. Let us take an example, because things little bit looks complicated. So, here suppose I want to have this same differential equation solver example, and this is that sequencing graph, and I have multiplied an ALU. So, ALU can execute addition, subtraction, comparison, all can be executed in the same block. And I say, I assume for simplicity that I have all the operations are single cycle. So, the DI value for each of VI is 1, right. If you have this and say my latency bound is 4, I want to execute everything in lambda is 4, right. So, that is something I want to solve. I will just see whether this is feasible or not, right. Now, if you find out the unique start time. So, unique start time is given by this. Now, the mobility will come into picture. For this source and sink operations, they are always scheduled in this, this is the for source and this is for sink. These are always scheduled in the last time. This is for lambda plus 1, right, because 4 and this is 0. This is always there, and I am going to schedule all these things from 1 to 4, right. That is what the way we model that sequencing graph. Now, this as I mentioned, this is from the ASAP to ALAP solution. So, now if you consider this operation 1, here ALAP and ASAP both give 1, right, because there is no mobility for this operation that we have discussed earlier. So, x11 must be 1, that means what, this operation V1 must start as time step 1. Similarly, for x2 also this x3 also this, because this is that critical path and there is no mobility here, all are 1, x4 and x5 till this point. So, x5 has to schedule in time step 4. So, that is why x54 is 1, but x51, x51, this x52, x53 all are 0, right. So, these are all 0. This is definitely giving this has to schedule in time step 4. And now, for the other operations, for example, say V11, mobility is here is 2, if you remember. So, this can schedule here, here or here, 3 is time step. This is the ASAP solution. So, V11 2, V11 x11 3 and x11 4, summation would be 1, because it can schedule anywhere, any one of these 3 steps. So, this is what is given by this. Similarly, for I can find out for all variables, right. So, this is my constant corresponding to the start time. Now, I will go to the precedence constant. Now, if you just take about this example, right, 1 to 3. So, now, this 1 to 3 is something just a minute. So, yeah, this is not mentioned here. So, let us say take this x7. So, for x because this is scheduled. So, let us take an V1 and this edge, right. So, what will happen, this schedule in 1 1 and this is scheduled in always this 1 3, this is 2, right. So, this is x 3 2, because this is always scheduled into x 3 and then this is something what is given by this, right. So, because this is always fixed, this is my x 1 1, this is x 3 3 and this is 1 cycle. So, this must be greater than or equal to plus 1, right. So, this constant I am going to get for this edge. Now, take a other edge, right. Say let us take this edge V6 to V7. Now, what are the possibilities of this V7? Sorry, V7 it can schedule in 2 or 3, right. So, V2 into 7 2 it will give you the time step or start time of this person 7, or 3 into 7 3, either it will start in time step 2 or time step 3, and for 6 it can start either in here or here, because there is a mobility of 1. So, 6 1, 1 into 6 1 and 2 into 6 2. So, this is what this part is nothing but this part is nothing but this, and since I have only one single time step. So, this is 1. So, I just put everything this side. So, this is 2 into 2 x 7 2 plus 3 into x 7 3 minus 6 x 1, this is moved here, minus 2 6 2 minus 1 is greater than or equal to 0. So, this is for all edges. Similarly, for all other edges also we can find out this kind of constants, right. So, these are listed only the non trivial one. Trivial one like this is you can find out. So, this is the set of constant for precedence. Now, if I assume that I have multiplier 2 multiplier and 2 ALU, I have to put constant for multiplier and also constant for this ALU, right. So, and the constant is given by this. So, this is about the type. So, for multiplier type, since these are all single cycle, I do not have that consider multiple step, I have to just consider the present state. Here the number of multiplier executed in time step is this 4. So, this x 11, x 21, x 61 and x 811 should be less than equal to. So, this actually ensures that all 4 will not be scheduled in time step 1, because your start time only out of this 4 operation only 2 of them can start at time step 2, because I have 2 multiplier. So, this is what is this constant signifies. Similarly, if you just go into the time step 2, this 3 2 6 7, and since this has a mobility, this also can execute here. So, 6 2 7 2 x 3 2 6 2 7 2, and also this also can execute, because this is there is a mobility. So, x 8 2 should be less than or equal to t. So, this combining these two, it will ensure that not all of them will be executed here, some of them will move back, some operation will move down. So, that all these resource constraints are satisfied. Similarly, for ALU, we can say that this operation has to be operation in this operation only this can execute. So, only this 10 1 less than or equal to 2, and operation time step 2, this can execute, this also can move down. So, this 3 can execute. So, x 9 2, x 10 2 and x 11 2 should be less than or equal to 2, and this way we can actually find out the constant for each ALU. So, how many constant will be here? For each multiplier, I have number for each time step I have a constant. So, there are lambda plus 1 number of time step into multiplier. So, this is a number of constant for multiplier and lambda plus 1 number of constant for adder. So, this is a number of resource constant will get from this resource constant. So, you can understand now I found I have find this is the set of constant, this is the dependency constant, this is my the precedence constants, and this is the resource constant, and if I solve this using this value, the value of all this x I will get. So, sum of this x I L value will be 0 and sum will be 1. So, this x 12 value will give you the start time step of each operation, which is nothing but the scheduling of that operation, right. So, if you just go into this is the solution I am going to get if you solve all this constant. You can see here I am actually that optimum solution that we have discussed in the last class, we are getting that because I have 2 multiplier here, 2 multiplier here. So, I am able to execute everything in 2 multiplier and 2 adder, still I am getting 4 times 10, which is the minimum possible value. So, this is if you just add these 3 constant and if you give to some solver, which will give you this solution, right. So, for this example now, this x 1 is 1, this is x 2 1 is 1, for this operation x 3 2 is 1, for this x 6 2 is 1. So, for this operation say x 5 4 is 1. You can see I defined that n into lambda number of variables. Out of this only this 11 for each operation only one of them will be 1, rest will be 0, right. So, this way and rest are 0, right. So, this is how the solution that solver will give you the solution. These are the variable 1 and rest of the variables are 0, right. This is what we will get, you understand, right. So, now if you just so ILP solution advantage is that we can use the standard ILP solution package, LP solvers or some solvers, and we can get a exact solution, right. So, we will get a exact solution, but the problem is, and also another advantage is that for a resource we add some constant, but we can also add some other kind of constant into the framework and it will still solve the problem, because this is a constant solver. But the problem is that it is not scalable. If you have say very in a large behavior, this may not work, because this is may not work for a big examples, right, big test cases. So, that is the problem with ILP solution. So, I will now move on to this next category of algorithm, which is heuristic based, but so before that I am going to talk about this Whose algorithm, which is there are some simplification assumed here, that each operations are unit delay. That means what? That each operation has to be executed in one cycle and all operations of same type. So, in practice all will be multiplier or all will be adder, but you can understand in practice not all operations are of same type, right. So, that means it does not actually applicable to the scheduling type problem, but this is the idea or the idea that is given by this algorithm will be taken in the heuristic based solution like list scheduling. So, we will just discuss here. So, this is a greedy and polynomial time solution. So, it will be a polynomial time solutions, and both can be this MLRC and MRLC both can be solved using this algorithm. And basic idea is that it maintain a value for each node, the distance from the sink node, right. So, if you just consider here, so now I just consider same differential equation solver example, but I assume that all operations are now of same type, say all are adder now, right. So, now I will just so this is my sink node, I am just trying to find out the distance, which is nothing but the critical path length, right. So, distance of this node is 1, distance node is 2, distance of this node is 3, distance of this node is 1, 2, 3, 4. For this node also 4, this is 3 because 1, 2, 3, 1, 2, this is 2, this is 1, 2, this is 2. So, I assume these values for each operations, right, and it maintain a priority list. Okay. It maintains a list of operations which is actually now available or can be scheduled, and based on the resource operations it select the operations which has the highest priority, and the priority value is this distance value, this 4, 4, 3, and it has a max. So, the variable which has a more value, which is more which has a higher priority than the other operations. So, it maintain that list. So, initially since all these operations depends on the input, these are all available, right. So, these all 5 operations are available, and they are put in priority list. Since this operation is 4, so 1, this 2, and this is 3, this is 8, and this is 10. The operation V 1, this is V 2, this is V 3, this is V 8, and this is V 10. So, this will be the priority list order, because these are the highest priority. Now, if you assume I have only 3 resources, so I am going to select the top 3 priority one, right. So, this is what I am going to do. So, this is the algorithm, I am not going to detail, but if you just have a working of this algorithm here. So, initially all this in the priority list, and say assume my resource is 3. So, I am going to select these 3 because they have the highest priority compared to these 2, right. So, now if you just after that these 3 are done. So, my priority list will be updated with this, so all the operations that are succeeding this operation will be now added, and now the priority list have this, right. So, order will be this way, right. Now, I am going to select these 3 because they are the highest priority. I should have select this instead of this, but fine, but this has to be selected. So, these are done. After that, then these 2 steps are done, then the next set of priorities this and this. So, this is what there, and I have 3. So, I can schedule all of them, and the next time, so I can schedule up this 4. Right. So, this is how the whole algorithm works. So, basic idea is that we calculate some priority value of each node, and then we try to schedule the operation which has the highest priority based on the availability of the resource. Right. This is how the whole algorithm works. So, now we will move into this list scheduling algorithm, which is nothing but than this enhanced version of this huge algorithm. Here this is also this, but here you can have multiple type of resource instead of only multiplier or only adder. You can have multiplier, adder, subtract, all kind of resource can be available, and your operations can be pipeline, multi-cycle, or other variations also possible. So, and we have some resource constraint, right. So, we can have both algorithm again, this MLRC that minimize resource or minimize latency, but we are going to discuss that minimize latency under resource constraint. The other can be understood from this discussion. Okay. But here the algorithm is that this particular solution does not guarantee to optimum solution, because it is a heuristic as algorithm. It does not guarantee that you will always get the optimum solution out of this, but this is something very fast, because this order of n time algorithm. You understand from the complexity of exponential, I have now polynomial time algorithm, linear algorithm. So, it will be very fast. Even if my solution is degraded by 10% or say 5%, is fine, because I am able to do this in very fast. For example, say I have a very big operations, I have a big behavior that ILP give you say solve in 1 hour, and this can solve in say 2 seconds. So, I will always go for this, because this is something is give you very fast, and in fact, in industry most of the industrial tool actually use list scheduling to execute this, do the scheduling in their internal tool. Okay. So, this is something is very popular algorithm which is widely used. Okay. And as I mentioned, it can actually work for different kind of resource, multi-cycle supports multi-cycle, pipeline operation, all can be supported. The only thing is that it does not give a optimal solution always, but give a very good solution most of the time. So, this is something which we will take it, because that is something is useful, because sometimes you have to finish everything on time. So, time is important, design cycle has to be minimized. So, list scheduling is widely used. Okay. So, we will discuss on that. We We will mostly discuss that MLRC problem, that means minimize latency under resource constraint, and we can have the different versions like this minimize resource under latency constraint, but we are not going to cover in this discussion. Okay. So, we have two kind of variables. First kind of variable is ULK, that means those operations, those predecessor operations are already executed, right. So, that means this is set of operations which of type k, because I have to now think about each type at a time, multiplier, adder differently, we are not going to merge them. So, when we are going to schedule multiplier, we are going to only schedule multiplier, when you are going to schedule adder, we are going to only schedule adder, and so on. So, we are going to consider set of operations Vi, which is stored in this ULK variable, this set, where all these predecessor operations are already executed. So, Vi to Vj, so these are the set of operations Vi, all these predecessor operations, those are edge when they are the predecessor operations, they are already executed. So, for this Dj is the number of time steps required. So, this is less than L. So, this is basically to say the number of operations whose predecessors, even if it is a multi-cycle or pipeline, they are already executed, and these operations set are ready, can be scheduled now, right. So, this is the priority list, the ready operations that can be executed. Similarly, I have a set of operations TLK, that means unfinished operation. So, that means those are operations that are running, that means they are started early, but they are still continuing in this Lth time step. So, if you just see that set of variable V, the operations V of type K, they are still this Ti plus Di greater than L, that means they are still, they have started somewhere early. So, this is my say time step L, they have started somewhere here or here, but they are still continuing here, right. So, these are set of operations that are running here, and what is important here is that I mentioned earlier also, these operations also need resource in this time step L, and these are the most important, they have to be scheduled, because they are already started, and we cannot start another operation by bypassing this operation, because they have started, they has to complete, then I can then only I can start other operations, and I can only start other operations if after scheduling all these such operations that are actually active in this time step, some other resources are available. So, the idea is that in a particular time step, these are the highest priority operations, they have to be scheduled, and if other resource available, I will take it from here based on some priority value, and priority value can be same as Hughes algorithm, the critical path from the sync node. Okay. So, this is the list scheduling algorithm. So, I am now going to do it for each resource type, right. So, say multiplier, adder and all, and this is UK is the set of operations that are available, right. So, the ready list, that means these operations are ready, their predecessors are done, and TLK is the set of operations that are unfinished, that means they are in progress in this particular time step. So, I have to schedule all this TLK plus some subset of ULK based on the such that this TLK plus SK is less than AK, AK is the resource bound, right. So, I will just select, so suppose my TLK has say 3 operations and ULK has say 5 operations, but my multiplier is only 4. So, I will take these 3 and only one of them from here. So, that I can execute all these 3 plus one of them here, right. This is how the whole thing works, and it ensures that this TLK is never greater than the AK, because I will not start any operation more than LK any time step. So, if I start from say time step 1, I always ensure that the number of running operation in any time step is not more than the resource bound, and then I am going to schedule all this operation in time step L, then I increase the time step by 1, right. This is how the whole thing works until all operations are scheduled. Okay. So, this is something is called list scheduling. As I mentioned again, I will maintain this priority list of finished operation, in progress operations. I will also maintain a priority value, which is nothing but the distance from the sync node, and I will schedule all the in progress operation first, and if further resources are available, I am going to schedule some other operations. Okay. So, let us take an example. So, in this example, you can see suppose this is my that differential equation solver again, and I assume that my D1 equal to 1, that is all are single cycle operations, and I have 2 multiplier and 2 adder. Okay. So, I have 2 multiplier and 2 adder. So, now what is U here at the start state, because I start from 1, all these operations are available, this V1, V2 and V10, this V1, V2, V6, V8 and V10, right. So, all are available. Okay. So, so this V10 is something is a adder. So, I am going to only consider the operations are multiplier type first, then the adder. So, I have only these 4 operation V1, V2, V6 and V8 are available. They are actually U, they are in the U list because they are now ready, right. So, their predecessors are sync node which is scheduled, and my T11 is null because there is no operation is running now, because I just start the operation thing, right. So, I am going to select this operation because the distance of this node is 4, distance of this node is 4, this is 2, this is 3, sorry, this is 3 and this is 2. So, I am going to, since I have 2 multiplier, I am going to select this and this. So, this is what I am just select V1 and V2, because I have to select, there is no Tij, there is no running operation, I am going to select all of them from this ready operations, and I am going to select these 2 because they have the highest priority. So, once this is done, my in the next step, because this is a single cycle, everything will be there, the Tj is not there because that is there is no running here, this is T I1, 2 1, 2 2, everything will be 0 because there is no running operation, all will be finished in the single clock. So, now I have this once this is done, this also available. So, my U will contain V3, V6 and V8, for this distance is 3. So, I am going to select this and this, not this one because they have the highest priority. So, I am going to select 3 and 6, and after that in the next time I am going to select 7 and 8. For adder, here I am only one operation is ready. So, I have V10, I am going to select it because there are 2 adder available, and the next time step I have this, only this is available, not no other. So, I have only V11. So, I am going to schedule it in time step 2, and then V time step 3 I have now V7 and V8 because now this 3 and 7 is done. So, 7 and 8 is now available and 2 resource. So, I am going to select both of them, and once this is done, now I have this and this both are available, let us say 4 and 9. 4 sorry V4 is only available, this is not available yet because I am going to do it now. I am going to do it in time step 3. So, now I am going to do V4 in the time step 3, and then finally V5 and V9 because there are 2 adders, I am going to schedule them into time step 4. So, this is what is going to give this list scheduling give you the solution, and you can understand this is also optimal solution because I am adding 2 multiplier and 2 adder, which is also given by the this list scheduling. Now, I will just consider the different variation of this. Suppose I might have a multi-cycle operations. So, all operations are 2 cycle, and again I have only 2 multiplier and 1 ALU, not 2 ALU. Okay. And now, I want to see how it can happen. So, initially as I mentioned this 1 3. So, for multiplier this 1 2 3 4, this V1, V2, V6 and V8 are available. Okay. And I am going to schedule this because they have the highest priority. This is distance 4, this is distance 4, this is 3, this is 2. I am going to select only this 2 V1 and V2, right. So, V1 and okay, sorry, I am sorry. So, I have 3 multiplier now. Okay. So, I have 3 multiplier, and the delay of the multi-cycle the multiplier is a 2 cycle operations and ALU is a 1 cycle operation. So, in this time step 1 I am going to select all this 1, 2 and 6. So, this will be progress, and this 10 for adder I am going to select this because I have only 1 operations. So, in the next time step this T now contain this V1, V2, V6 because they are all are running. So, even if my U contain this V8, that finished operation, this operation type 1 time step 2 a V8, I cannot schedule it because all are running here. So, even if I have some ready operation, I cannot schedule it because they all are running. So, in the time step 2 there is no operation executed, only this operation 3 will continue the multiplier, and since this is already done in time step 1, I can do this V11 here, right. So, this is what I have done. So, in time step 3 now all this operation finished, right. So, my T list is null, and once they are finished in my U list, this V3, V7 and V8 all are there, and the distance this is 3, this is also this is 2 and this is 1, but I have 3 multiplier, I can start all of them, right. So, 3, 7 and 8 are starting in my time step 3. In time step 4 I have to carry out this because I cannot do anything else. So, in the time step 4 these 3 will be executed, and no other addition operation will be there because these are all pending. Until this is done I cannot start. Then after that in V5 once the T4 they are executed, execution is complete. In T5 I can do this, T6 I can do this, and T7 I can do this. So, I need 7 time step to execute these operations where my multiplier are 2 cycle operations and I have 3 multiplier, and this is also the list scheduler will give you this solution. And if you know the pipeline one, just briefly I will talk about. So, say multiplier, there are 3 multiplier and there this multiplier is 2 stage pipelining. So, again I will start these 3 because there are 3 multiplier available. In the next time step I could have started another 3, but I have only one multiplier is ready, right. My V t this U list only contain V 1 2 contain only V 8. So, I can only start this as a pipelining with any of them, right. So, after time step 3, so after in time step 2 this all 3 are finished, this is continuing. So, and there are 2 operations are now available. So, I can actually schedule all of them because I have 3 multiplier. So, I can just start all these 3 in the time step 2 and so on. So, this is how I can, if I do this pipelining manner, I will take 6 times to execute this, where I have 3 multiplier available and this all multiplier are pipeline, 2 stage pipeline algorithm. Okay. So, with this I finish the discussion on scheduling. As I mentioned, all these scheduling algorithms are NP complete. So, exact solution is not scalable, we can have ILP solution, but smaller, this always give you the optimal solution, you do not have to worry about this. But we usually prefer the heuristic based algorithm, because that is something very first, polynomial time, order of n, least scheduling, and that also give a very good solution most of the time, right. So, this is something in the scheduling part. Okay. So, we will now try to talk about this allocation and binding and their automations of allocation and binding. So, as you mentioned, in this allocation and binding we try to map those operations into function unit and variables to the registers, right. So, this is and try to optimize, and our objective is something, try to use maximize the resource sharing, that means use minimum number of resource, right. That means minimum number of registers, minimum number of function units. So, that is our objective. Okay. So, let us take an example. So, suppose this is my the schedule generated by some scheduling algorithm, where operation 1 and 2 schedule in time step 1, operation 3 and 4 schedule in time step 2. So, what is the optimum hardware here? I have to use 2 and all are say type adder. So, I need at least 2 adder to do this, because this 1 and O2 is running in time step 1. So, I can schedule O1 here, O2 here, and now in the time step 2 I can do O3 in this time here itself, because this is now free, and I can do this in this this, right. So, I can schedule O1 and O3 in the adder 1 and O2 and O4 into this. So, I need 2 adder, right. So, this is the minimum number of resource possible for this. Similarly, for registers I need at least 4 registers for storing these 4 variables. So, I need say R1, R2, R3 and R4, and A is stored here in R1, B is stored R2, C is stored in R3 and D is stored in R4. And now, after time step 1 E is available, A is still using. So, this is still we need A, but B is not required. So, I can store E in B, right. I can store in the same register in R2 B E, right. Similarly, here D you are going to use here, but C is not required. So, I can store F in the same register as C, right. So, I store F here. So, after this, again once this ready, this my G and H variable is required, but again this all E and F is dead now, I do not need. So, I can store again G in this same register R3 and H in this register. So, I need 4 register minimum to store this. So, I have 1 2 3 4 6 7 4 5 6 7 8 register 8 variables. I can store them in 4 registers. I can store them in 4 registers, and I have 4 operations. I can execute in 2 FU, right. So, that is what is the minimum thing. So, now the question is how we can automate this particular process, right. So, to do this we try to find out some conflict graph or compatibility graph. Let us find out that. So, what is conflict graph? So, I will do the same thing for FU register is the same way we can do. So, we will just talk about that FU allocation and binding, and the register allocation the same process, which will follow the same kind of algorithm. Okay. So, what is the conflict here? So, O1 and O2. So, for each operation I will draw a node. Okay. So, this is my operation 1 O1, this is O3 2, this is O3 and this is O4. Okay. And now, O1 and O2 has a conflict. Conflict why? Because they are going to be scheduled in the same time step. So, I cannot do them in the same adder, right. So, I have a conflict between them. So, I will add a edge. Similarly, O3 and O4 has a conflict, but there is no conflict between O1 and O2 and O3 to O2, similarly O4 to O2 and O4 to O1. So, I have this is the conflict graph. Okay. So, this is what is conflict graph. Okay. Similarly, I can construct a compatibility graph. What does it mean? Which operations are compatible to each other, that means they can be shared the same resource. Okay. So, to draw the compatibility graph out of it, I can try that again. So, this is say operation 1, this is 2, this is 3 and this is 4. So, operation 1 is compatible with 3 and 4 because they are in different cycles. So, 3 and 4. Operation 2 is compatible with 3 and 4, right, 3 and 4. And operation 3 is compatible to 1 and 2 and 4 is operation compatible. So, this is the graph I am going to get. This is compatibility graph, right. So, this is the compatibility graph I will get if I draw this, right. So, from this schedule behavior we can either construct conflict graph or compatibility graph. And then what does it help? How does it help? For a compatibility graph, we try to, so what does it mean? If there is age, means they are compatible, they can be scheduled in one time step. In the same, sorry, they can be scheduled using same adder or same resource, right. So, if I have this, then they can be scheduled in this, right. Similarly, if there are 3 nodes and they are all compatible to each other, they can be also can be scheduled into the same resource. They can be executed in the same resource. Or if there are 4 nodes and they have compatible to all each other, then also these all 4 can be scheduled into the same they can be executed in the same resource. Similarly, if I have 5 node, if I can find such node where all are basically compatible to each other, this is nothing but a complete graph. So, what I am drawing here is nothing but complete graph of node 2, this is complete graph of node 3, this is complete graph of node 4, this is complete graph of node 5. So, if you can find such component, that means they are all compatible to each other, that means they can share the same resource, then the same that particular all these things can be mapped to a same resource. So, in the compatibility graph we have, and this is a complete graph subset, right, and this is called clique. Okay. Clique is what? Complete subgraph of a big graph. So, in the original graph there may be say 100 nodes, and out of that I find 4 nodes, they are compatible to each other. So, that is a clique, maximum subgraph, complete subgraph of a big graph, right. So, this is nothing but once you have this compatibility graph, this is nothing but you have to find the all cliques of this your compatible graph, and your compatible this clique, each clique will be mapped to a same resource, right. So, this is kind of a clique partitioning problem. So, or minimum clique cover problem. So, either clique partitioning means you try to cover all your graph using some cliques, so that all of your nodes are covered, right. So, for example, in this for this graph, if you complete the, so construct the compatibility graph for multiplier, this will be the compatibility graph, and if you construct the compatibility graph for this adder, this will be the compatibility graph. Okay. I will just explain for this 3, operation 3 here is not compatible with 6, but it is compatible to any other multiplier, right. So, for 3 it should be from 1 to 7 and 8, from 3 there is node from 1 to 7, 8 and 2. So, 3 is compatible to all other operation except 6. Similarly, for 1, this is not compatible to 2, but it is compatible to any other operation. So, this is how we will construct this, and for each type I have to do this, because I am not going to club multiplier and adder into same resource, right. So, similarly, for this ALU, so these are all scheduled in different time step, right. So, all are scheduled, only these are not compatible, 5 and 9. So, all other are compatible. So, this 10 is compatible to all others, right. So, from 10 you have S to 11, S to 11, S to 5 and 9, from 10 to 5 and 9, and then I have also S to this 4, right. So, it is connected to this. So, this way I can actually construct the compatibility graph, and then you have to apply this clique part is a clique cover problem, which is very well known graph problems. So, you can actually apply this to find out the minimum number of cliques, that is it cover the whole graph, and each clique is nothing but one resource, right. For example, here you can find it here is, so in this graph you can see that these three nodes, because all are multiplied. So, this is a complete graph. I have only a complete graph of size maximum size 3, there is no complete graph of size 4 here, because if you add one of them, if you add this to this node is not there, right. So, I cannot have a size 4 clique here. So, I have 2 cliques. So, this is 1 clique, this is 1 clique. So, this will be multiplier 1, this is multiplier 2. So, I need 2 multiplier to this to execute, and you can understand in multiplier 1 I am going to map 1, 3 and 7, 1, 3 and 7. In multiplier 2 I am going to map 8, 6 and 2, 2, 8 and 6. these 3 I am going to execute in 1 and this is going to execute 1. So, this is how I am going to solve this problem. So, the one approach is that you construct the compatibility graph and you apply this click covering problem to find out all the clicks, and each click is mapped to a single resource, and all the operations will be can be executed in that particular resource. Okay. This is something we can do in one way, and conflict graph is something, as I mentioned, if these two operations are, this is just the reverse graph of this. Reverse graph means what? You just remove all the edges here and you add all the edges that is missing here. So, that will give you the conflict graph, right. So, here also I can construct from this behavior, I have a edge in the conflict graph 1 to 2, right. I have a edge from 1 to 2 and this 3 to 6, right. So, I have only a 3 to 6 and 7 to 9, because they are all executed. I am talking about the multiplier. So, I should have this 3 A's should be there, right. So, these 3 A's should be there, and now once you have this, what algorithm you can apply? You can actually use this graph coloring problem. This problem can be mapped to graph coloring problem. What? So, what is the graph coloring problem? You try to find out the minimum number of color to color all the nodes of the graph such that two adjacent nodes have a different color. So, that is called this chromatic number. Okay. Chromatic number is the minimum value of color. So, which is required to color all the nodes of that graph such that two adjacent nodes have a different color. So, what does it mean? So, if you just do this, so you can apply say blue here and this say yellow, because they have a edge between this, and then edge between. So, I can apply blue here and yellow here because there is a edge. This I can apply blue or yellow because there is no edge between this. If I apply blue here, it has to be yellow, and if I apply blue here, this has to be yellow. So, I need 2 here, right. So, there are two color is sufficient to do this, right. So, now if all the node have the same color is nothing but they can be mapped to the same resource. So, you can see here this also give you the solution like 1, 3 and 7, 1, 3 and 7 is mapped to this the same resource, here also 1, 3 and 7. So, both are same problem, but you have a different approach. One is click covering problem, otherwise is graph coloring problem, and here also this 2, 6 and 8, here also 2, 6 and 8, 2, 6 and 8 is the map to the same multiplier, right. So, here also it give you, since the chromatic number is 2, that means you will say there are 2 multipliers required, and this 1, 3 and 7 is going to map into multiplier 1, and 2, 6 and 8 going to map into multiplier 2. Similarly, for adder, this is the complementary graph for this multiplier. So, you can see that the results is same, right, but you can apply 2. For conflict graph for adder, I have this is the only thing, because there is only sharing here, and I can use white for all these 4 and only this is yellow. So, I need 2 adder, and this 4, 10, 5, 9 can be executed in the same adder, and this is adder 1 and this is adder 2. Right. So, here I just discuss how that finding minimum number of this FU function unit can be mapped to a graph coloring problem or compatibility graph problem, and apply those conventional graph coloring problem algorithm or say heuristic or say comparative click covering heuristic to solve this problem to get this solution. Okay. So, this is one approach, and now the register binding problem is the same, right. So, as here when this node, each node will be registers, we can actually construct a conflict graph or a compatibility graph. How? If the lifetime of 2 registers are overlapping, then there is a conflict between them, right, and if they are not overlapping, there is no conflict. So, I can construct based on that idea, I can construct the conflict graph or compatibility graph from the register lifetime information. Similarly, I can also find the interval graph, and I can apply any of the technique that I have discussed so far. So, to solve this register binding problem as well, right. So, this is also same problem, just here the each node will represent the registers, the V is the set of variables, and E is the overlap. If they are lifetime overlap, then I will add a H, and then I can construct the interval graph or complete graph or compatibility graph, and you can apply the same algorithm. So, both can be solved in the same approach. I will just go to the last part, that data path and control generation, which is very obvious, there is no much complicated here. Yeah, so, here as I mentioned that after this register allocation binding and function unit binding, I know this operation is mapped to this, and these are the set of inputs possible here, these are the set of input possible here, and I have to make some connection here, interconnection, so that this operations can be executed, and in some time step I need this and some time step I need this, some time step I need this, and so on. So, I need to add some data path interconnection unit like multiplexer, demultiplexers and on so on, so that I can execute this operation smoothly, right. And there are two possible operation, bus based architecture or mux based architecture. So, in bus based architecture what happened, for each register there is a output bus, right. For register 1 there is a bus, for register 2 there is output bus, for register there is output bus, and if this R1 is connected to this, I will just add a connection here and add a switch here. Similarly, if say this R4 is connected to this, I will just add a line from here and for R2 and then I just add a switch, right. So, this switch will be controllable by a control signal. So, if in a time step 1 says I am doing say I am doing R1 plus R2 equal to R3, then this switch and this switch will be activated in time step 1, right. And in other time step, if say R4 and R5 is happening, then the switch corresponding to R4 line and the switch corresponding to R6 line will be enabled in that particular time step. Okay. So, that particular register value will come to the FU. So, this is bus based data path, and mux based, which we have discussed in the last lecture, that we have mux, will put mux at the input of the FUs, we will put mux at the input of the register, which we have discussed, and then we will add control signal, so that I can control the data flow this versus this based on the operation going to execute in that particular time step. So, both are possible and both are kind of same. Here mux, here only switch is nothing but 2:1 mux. So, both are possible and we can generate any of them. Okay. And here what kind of optimization is possible? Actually that commutative operations can be applied here to improve the this mux size. So, if you just see here, so for example, say time step 1 this I1 is coming, time step 2 R2 is coming, time step 3 R3 is coming, time step 4 R5 is coming, and similarly here R3, R1 and R2, right. And similarly here also, right. And here also this value in time step 1 and 3 go to R2, time step 4 it goes to R6, time step 2 is going to R5, the output of this adder. So, we will add, so conventionally what we are going to do, I will just put a mux 4:1 mux, there is control signal length will be 2, here also 4:1 mux, control signal will be 2 bit control y and so on. So, this is the data path I am going to generate blindly if I generate the data path. Similarly, here since there are two output which so they are all connected, so there is no problem, but if there is a multiple, so adder this also coming here, then I have to put a mux here, right. So, this is what I have generated here, right. So, this is something is known. Now, if you just see, if I just do here, I just swap this R2 and R1 and you will get this, right. So, I just swap this R2 and R1. Okay. So, now you can see initially I have this R1, R2, R3, R5, and if I just move this swap this R2 and R1, what will happen? We can see R2 comes here and R1 comes here, and now I have 2 R1, right. So, I can select this R1 and R1, here I have 2 R1. So, I can reduce the mux size. So, I have only 3 possible input R. So, there are 2 R3 also. So, and also I swap this I1 and R3. So, this also I swap, because I am doing A plus B, right. A plus B and B plus A is both are same. So, I can just swap this A and B and B to A. What is done here R1. So, here you can see I actually am doing in time step 1 I am doing I1 plus R3, right, equal to R2. This is what I am doing here, and this time step 2 I am doing R2 plus R1 and it is storing into R5. Time step 3 I am doing R3 plus R1 and it is storing in time step 3 R2. And time step 4 what I am doing, this R5 and R2 and it is storing into R6. So, this is the 4 operations I am executing here. So, similarly can be done here, I am not going to that detail. So, now what I am just doing, I am just swapping this. So, instead of R2 plus R1 I am just doing R1 plus R2, they both are same, R1 plus R2. Similarly, here I am doing L1 plus R3, instead of doing I am just doing R3 plus I1, right. So, I just swap this to commutate this operation, right. If we just do this, what will happen? You can see now I just do this. So, now I have 2 R3 here, 2 R2. So, I can actually reduce the size to 4:1 mux to 2:1 mux, because I am now actually only 2 possible input. Here also I mean one of the input to reduce. So, similarly, I can do the same thing for this mux, which I am not going to discuss detail, and reduce the size. So, this is the kind of optimization we can do in the data path generation. using these commutative operations and all, we can actually reduce the mux size, which will also give you the overall area requirement of the whole design will be less, and also the number of control signal required also less. Earlier I need 4 bits, I mean 2 bits, I am now only need 1 bit. So, the controller also size also will reduce. So, this is the kind of interconnection optimization we can do, and then finally, we just add those control signals to this all these muxes based on the size, right. So, this is so in the control and data bus generation steps, the steps are kind of obvious. You have to make add mux or bus there, and you have to put switches or muxes, and then you can actually apply this kind of commutative operations or associativity and all those kind of operations just to reduce the interconnection size. So, these are the possibilities here. Okay. So, now we will come to the summary of these steps. So, we found that all these steps, scheduling, allocation, binding, all are kind of NP complete problems. So, exact solution is something is not asked for most of the time. So, you apply usually a heuristic based solution like list scheduling and I mean used to solve this problem. And another important factor here is something, all these subtasks are kind of interrelated. If you have a different schedule, your register allocation or binding, the number of registers is required or a function is required will be different if you have another version of the scheduling, right. So, all are kind of interrelated. So, you need to explore the design space as much as possible to give you the best results. And if you just see into the industry, there are various in the synthesis tools is available like Vivado from this Xilinx, or say SMC and Symphony model compiler, or SCC the C compiler, both are from Synopsys, Catapult HS from Mentor Graphics, or say Quartus from Intel, which is basically Alter. So, all these tools are matured and they are available, and they have been is kind of widely used in the industry, and so high level synthesis is a very exciting area, but still there are much more thing can be done, which we will discuss in subsequent classes. So, in tomorrow's class we are going to discuss about what is the good way of writing C. As I mentioned in the first class also, that not all C will going to give you the good synthesis results, right. We have to write the loop in specific way, or say write that array into specific way, access them in a different way. So, those we are going to discuss what is the good way of writing your operations or the behavior in C, which will actually which will generate a good hardware or good RTL through this synthesis tool. So, that will be the topic of discussion in the next class. Thank you.